Hi everybody, in this video I'm going to use a Taylor series expansion to derive a really useful equation for an object moving in one dimension with constant acceleration. In this equation, the symbol v represents the one-dimensional velocity that the object has when it's at position x. The symbol v sub 0 represents the one-dimensional velocity the object had when it was at position x sub 0. And a represents the constant acceleration. Keep in mind that the definition of the velocity is the derivative of the position with respect to time, and the definition of the acceleration is the derivative of the velocity with respect to time. In the course of this derivation, we're going to need to use the chain rule for derivatives, so I've written it here for when we need it. Now, this equation is normally derived by first deriving other equations that depend on time, and then using those equations to eliminate the time and get this equation. It's the elimination of the time that makes this equation so useful, because it allows us to calculate the square of the velocity at any position without any knowledge of the time, provided that we know the constant acceleration, and if we know the position and the velocity at some earlier point in the motion. In this video, I'm going to derive this equation by expanding v squared, which is a function of x, about x sub 0 in a Taylor series expansion. I think it's really interesting that this can be done, which is why I'm making this video. All right, here we go. I've started us off by writing the Taylor series expansion of some general function of x, call it f of x, about some particular value of x, call it x sub 0. I've written it out in summation form right here, and I've written it out term by term here. Anywhere you see the brackets with a little x sub 0, that means to evaluate whatever you see in the brackets at x sub 0. Now, the particular function of x that we want to expand in a Taylor series expansion about x sub 0 is v squared of x. So what we can do is everywhere we see an f, we can put in a v squared. So I'll do that right now. Now, let's work through this term by term. V squared of x is just v squared, where now the x dependence is implicit. V squared evaluated at x sub 0 is just v sub 0 squared. I've got my plus sign. And now let's take the quantity in this bracket and put it down here so we can work through it. Now, here's where we need to apply the chain rule. The chain rule says that the derivative of some function with respect to x could be written as, for example, the derivative of that function with respect to t multiplied by the derivative of t with respect to x. And that's exactly what we want to do here. So the derivative of v squared with respect to x can be written as the derivative of v squared with respect to t multiplied by the derivative of t with respect to x. Okay, let's keep working through this. The derivative of v squared with respect to t is going to be 2v dv dt, and that is going to be multiplied by the derivative of t with respect to x. Well, the derivative of t with respect to x is just the reciprocal of the derivative of x with respect to t. Derivative of x with respect to t is the velocity, so the derivative of t with respect to x is just going to be 1 over the velocity. All right, one more step. V divided by v gives us 1, and the derivative of the velocity with respect to time is the acceleration, so we're going to have 2 times the acceleration times 1. Okay, so the derivative of the square of the velocity with respect to x is equal to 2 times the acceleration. We need to plug that in here. Now, so this is 2 times the acceleration. That needs to be evaluated at x sub 0. So all of this, not including this, but this evaluated at x sub 0 is 2a sub 0, because the acceleration at x sub 0 would be a sub 0. Now, what we can do is we can apply our constant acceleration condition. So I'll write that out here. And since the acceleration is constant, that means the acceleration must be equal to its initial value. So 2a sub 0 would just be 2 times the constant acceleration. And then we'll have this term here carried down, x minus x sub 0. And it looks like we're done. But in order to make sure that we're done, we have to verify that these terms vanish in the case of constant acceleration. So let's do that now. Let's take this term right here and put it here so we can work with it. The second derivative of v squared with respect to x will just be the derivative with respect to x of the derivative of v squared with respect to x. Now, the derivative of v squared with respect to x, we've already worked through that. That's 2a. All right, so I've got the derivative with respect to x of 2a. Now, if the acceleration is constant for an interval of motion, that means it's constant with respect to both time t and position x. So, if the acceleration is constant, then the derivative with respect to x of the acceleration is equal to 0 if the acceleration is constant. So in the case of constant acceleration, this quantity is 0, and that kills off this term of the sum. I need to emphasize that by 0, I don't merely mean momentarily 0. I mean 0 and constant. That is, in the case of constant acceleration, the second derivative with respect to x of the velocity squared is 0 and constant. Now, since the derivative of a constant is 0 and constant, that means that the derivative with respect to x of this quantity will also be 0 and constant. And the derivative with respect to x of the derivative with respect to x of this quantity will also be constant, and so on and so on. That is, all higher order derivatives of the velocity squared with respect to x will be 0 and constant. We can express that formally right here. Now, since this and all higher order derivatives of the velocity squared with respect to x vanish in the case of constant acceleration, that will kill off this term of the sum and all subsequent terms of the sum, leaving us only with this, which we showed earlier was equal to this in the case of constant acceleration. All right, we've done it. We've shown that this important equation for one-dimensional motion with constant acceleration can be derived by expanding the velocity squared as a function of x in a Taylor series about x sub 0. That's all I've got. Thanks for watching.